Hello, everybody, and today we will. So I will give you the lecture number 8. Chalk. Today there is lecture number 8, and it will be devoted to zeros of solutions. Okay, this topic is very important in applications. So today we will consider scalar differential equations with variable coefficients. I mean the equations of the form x double prime plus let it be p of t x prime plus q of t equals 0. Okay, so where p of t and q of t are two continuous functions, and they are defined on some interval I. Included in R, so on some interval. So we are able to solve the equations of this form when P and Q are constants, and if P and Q do not depend on T, if they are constants, we are able to solve them, to solve this equation. But if P and Q are variable functions, then it is impossible. So very often, most of the time, it is impossible to solve this differential equation. But we want to make a qualitative analysis of these solutions, and today we will be interested in the zeros of solutions, of this equation. It is related to oscillations of solutions. So if we will be able to study their structure, so the nature of zeros of solutions, we will be able to describe the oscillations of solutions. So you can see the zeros of solutions. And we will speak about, so if we have time, we will speak about the fact that if we have two different solutions, linearly independent solutions of the same equation, then zeros of these solutions will alternate. And so if we have obtained an oscillation of one solution, we will have, so we will know that any other solution will oscillate in the same way. Well, and so today we will speak about Sturm theorem, Sturm comparison theorem. But let's start to study the equations of this form. And first of all, so we will need some definition. So definition 1. Since we will speak about the zeros of solutions, so we will need the notion of a simple zero, or so a simple root or simple zero of a solution, and a multiple root. Okay, so let x of t be twice differentiable function b of class. So maybe so not twice differentiable, b of class. So it is enough to have class C1 on I. Then, so if x of t0 equals 0, but x prime of t0 is not 0, then T0 is called a simple zero. Or a simple root of a solution. So T0 is included in I. And if x of T0 equals 0, and x prime of T0 also is also 0, then T0 is called a multiple 0. Or multiple root. So this definition is consistent with the definition of simple and multiple roots in the theory of polynomials, right? For polynomials, similarly, we know that a simple root is a root so if Pn of x is a polynomial, then x0 is a simple root if P of x can be represented as the product x minus x0 times the polynomial g of x, such that g of x0 is not 0. So this is a simple root. And this is the same as to say that Pn of x0 equals 0 and the derivative is not. So this is a simple root, and multiple root is again the same as to say that Pn of x0 is 0 and the derivative of x0, the derivative of this polynomial at x0 is also 0, right? So this definition matches one for one of simple and multiple zeros for polynomials. Well, and in what follows, we will need the following lemma, and we will start with lemma 1. Okay. If x of t is a solution of the differential equation, so this is equation number 1, let it be equation number 1. So if x of t is a solution of 1, then for any closed interval J included in I, closed interval means something like AB. This is the closed interval, right? So for any closed interval included in I, the zeros so the solution x of t has finitely many zeros in AB and in J, which is equal to AB, finitely many zeros. They are isolated, finitely many isolated zeros. And all the zeros are simple. All the zeros are simple. Well, so this is a statement. And now I will prove this statement. I will start to discuss so the last fact, simple or multiple roots. Simple or multiple. So suppose T0 included in AB is a multiple root This means that x of t0 equals 0 and x prime of t0 is 0. But we remember that x of t is a solution of equation number 1, of equation 1. And so we can consider an initial value problem. So consider an initial value problem. x2 primes plus p of tx prime plus q of t equals 0 and x of t0 equals 0 and x prime of t0 equals 0. This is an initial value problem. Okay, so I should use, so I should add something. So non-trivial solution, let it, is a non-trivial solution. If the solution is trivial, so this means that x of t is identically 0, then all the points of this segment will be multiple zeros, of course, not finitely many, of course, all the points will be zeros. So for a non-trivial solution. But if we speak about a non-trivial solution, then, so this is impossible for a non-trivial solution because we can see that the function x of t, which is identically 0, satisfies this initial value problem. But by the Picard-Lindelof theorem, the solution is unique. So this is a solution of this initial value problem, and no other non-trivial. And this initial value problem cannot have a non-trivial solution. So this is a contradiction with this assumption, with this hypothesis of our lemma. So it must be a non-trivial solution. So this fact proves that it cannot be, the 0 cannot be a multiple 0, only a simple 0, right? So we can see that it follows from this that any 0 of the solution is a simple 0. Okay, step number 2. Suppose we have infinitely many zeros on AB. So we assume that x of t has infinitely zeros on AB. But we know that by Balzano-Weierstrass theorem, there is a convergent sequence. So it has a convergent subsequence, right? So if we consider the sequence of zeros, then by Balzano-Weierstrass theorem, there is a convergent sequence. Tk, and it converges to some number t0, which is in AB. This follows from compactness of the closed segment. Okay. We know that x of tk equals 0. Since we know that x of t is a continuous function, x of t is of course a continuous function because it must be twice differentiable. So it must satisfy this equation. So it must be differentiable and twice differentiable. So it is continuous. By continuity of this function, we can see that x of t0 is also 0. Well, and now we want to come to the contradiction. So to show that we come to the contradiction, I will use the mean value theorem, Lagrange's mean value theorem. Mean value theorem says that the function, if the function is differentiable in the interval and continuous, okay, so I'd like to recall the mean value theorem. So if f of t, f of t is continuous on the closed interval AB, let it be alpha beta, then differentiable in the open interval, and okay, then f of beta, then there exists C in AB. So I have not enough time to, or enough space to continue. Okay, differentiable in alpha beta, right here. Then f of beta minus f of alpha equals f prime of c times alpha minus times beta minus alpha. So this is a mean value theorem, and I'd like to apply it. Yeah. Now let's consider the segment between tk and t0. Okay, for definiteness, let's assume that tk is less than t0. So on this segment, the function, the solution x of t is continuous and differentiable, and so we can apply the mean value theorem to this closed segment, and we can see that it is x of tk minus x of t0 equals x of tk in some point, at some point tk asterisk, it is in the segment tk, so t0, it exists, times tk minus t0. But we know that x of tk is 0 and x of t0 is 0. So they are 0 by our assumption. So this is 0, but this is not 0, and so x of tk asterisk must be 0. So it is 0. Okay, so we know that tk approaches x0, tends to x0 as k approaches infinity. but tk asterisk is between tk and x0, so it is t0, right? Tk asterisk is between tk and t0, and so it is also, so this sequence also approaches t0, and the derivatives of our function, and at these points the derivatives are 0, and this yields that this implies by continuity of the derivative of x, this implies that x prime of t0 is also 0. So we can see that x of t0 is 0, and the derivative of x at t0 is 0. These two facts contradict the first step. So we have proved that it is impossible for a non-trivial solution, but we have this. So this contradicts our assumption that x of t has infinitely many zeros on the segment AB. Well, so the lemma is proved. This proves the lemma. Well, and we go further. Let's go further now. So we will need lemma number 2, lemma 2. So or maybe, so shall I speak something? No. So now lemma 2. Okay. So in what follows, I will need the substitution which reduces our equation, this differential equation, to the second order differential equation with a zero coefficient p. So the following substitution, so by a substitution, u of t, which is equal to x of t times e to the power 1/2 the integral of p of t dt. So the equation 1 reduces to the equation u 2 primes t plus so it's better to becomes, so it becomes u2 primes plus u of t, u equals 0. So it is possible to eliminate this term, the second term. So this substitution reduces the second term to 0, and our equation becomes so has this form. So where u of t equals u of t minus something. I have forgotten the formula, so we will write this formula after we prove this lemma. Let's prove the lemma. And so in addition, we can see that the zeros of the function u of t and x of t are the same, right? Because x of t is multiplied by something positive, and so the roots, the zeros of x of t are the same as the zeros of u of t. And so in what follows, we will use this fact. We will simplify our equations to the equations without the second term. And this substitution preserves the zeros of our function. Okay, so minus something. Let's do this substitution, and so it is. So this lemma is technical. So let's take a derivative of this function. Let's differentiate, and then differentiate twice. So so u prime will be. So we will use the product rule to differentiate this, and we will get x prime times e to the power 1/2 the integral p dt plus x times the derivative of this function times 1/2 p. So the chain rule here. So just differentiate the power of the exponent of the number e, and we will get 1/2 p. So this is the first derivative, and the second one will be u2 primes will be differentiate this. It will be x2 primes times e to the power 1/2 the integral p dt plus the derivative of the second term, second factor, will be e to the power 1/2 the integral p dt times 1/2 p. Well, so this is the derivative of the first term. Next, plus, and let's differentiate this. So, but it involves three factors. So we will use the chain rule to differentiate this. The derivative of x, so plus x prime times e to the power 1/2 the integral p dt times 1/2 p plus, we'll use this space, so plus, then let's differentiate this. So I will rewrite x, then differentiate this, e to the power 1/2 the integral p dt times the same factor. So, and it will give us 1/4 p squared plus x times e to the power 1/2 the integral p dt times 1/2 p. So p prime. So the last term, so here we differentiate the last factor, right? So since this product involves three factors, then the chain rule will give us three terms, 1, 2, and 3. Well, next, let's collect similar terms. So these two terms are the same, so we can add them together, and we will get the following. u2 primes is equal to x2 primes e to the power 1/2 the integral p dt, then plus 1/2 p plus 1/2 p will give us p times x prime e to the power 1/2 the integral p dt plus, so I will collect similar terms here. It will be, so the common factor for these two terms is x times 1/2 the integral p dt, 1/4 p squared plus 1/2 p prime. Well, we can see here, so these two terms can be written as x2 primes plus px prime times e to the power 1/2 integral p dt. So we can see that u2 primes equals this plus, and this is u. Squared plus 1/2 p prime. Just rewrite this. Okay, now let's look at equation number 1, this equation. We can see that x2 primes plus p of t times x prime is equal to minus q of t. So we can see that this follows that x2 primes plus px prime equals negative q. Oh, sorry, so I have forgotten to multiply by x. So q of t times x, of course. Qx. Well, so I will rewrite it as u to double prime equals minus qx times e 1/2 p dt plus u 1/4 p squared plus 1/2 p prime. And I will replace this by u, which is also u. And we can see that our equation becomes u2 primes equals minus u times q plus u times 1/4 p squared plus 1/2 p prime. And we can rewrite our equation as u2 prime double prime plus. So if we move these two terms to the left, we will get the following: q minus 1/4 p squared minus 1/2 p prime times u equals 0. Okay, and if we denote this term by q, we will get the equation u2 double prime plus q of t u equals 0. Okay, so lemma is proved. And so I will finish the formula. So q of t is equal to q of t minus 1/4 p squared minus 1/2 p prime. Okay, so this is lemma, and
okay. Will we have a seminar for A today, or we won't have seminar A?
So I will prove the theorem, and after this I will stop our lecture. Maybe it will be shorter than usually. And after this, I suggest, do you want a break, or maybe I will prove theorem, and after this we will have a break. After this, I will solve something using the variation of parameters, and okay, and after this we will have control work, control test.
They were not going to do seminar.
So no seminars today. So the control work on this seminar. There will be a control work. Well, let's prove theorem, and after this we will have something else. Well, So maybe I will start with this part of the blackboard. Theorem. It is called the Sturm comparison theorem. Sturm comparison theorem. Okay, so we consider, or maybe I will start with the word consider. Consider two equations of that form of form 1. X double prime plus p of t x prime plus q1 of t x equals 0. This is the first equation. And the second equation will be y double prime plus p of t y prime plus q2 of t y equals 0. Okay, where p is of class C1, q1 and q2 are of class C, and q1 is less than or equal to q2. Okay, let's compare these two equations. So we have the same beginning, so x double prime and y double prime. P, so the function p of t is the same in both equations, and q1 of t and q2 of t are different, and we suppose that they are related by this inequality. q1 is less than or equal to q2 for any so of t for any t on the interval I. So then between any two zeros of x of t of the first equation, zeros of a solution of equation, let it be equation 2 and equation 3. Between any two zeros of a solution x of t of equation 1 or of equation 2, there is so there is a zero, so at least one zero y of t of equation 3. So step number 1. First of all, I will reduce both equations to the equation to the equations that do not contain the second terms, right? So by the substitution u equals x times e to the power 1/2 the integral p dt, and v, which is equal to y times e to the power 1/2 the integral p dt, we reduce both equations to the form u double prime plus q1 of t u equals 0 and v double prime plus q2 of t v equals 0. And we can see that q1 of t is less than or equal to q2 of t. Because of the formula given here, so you can see the formula for the u function q of t, it is equal to q lowercase of t minus 1/4 p squared minus 1/2 p. So these two terms will be the same in both substitutions, and so if q1 of t is less than or equal to q2 of t, if this is true for lowercase, for functions small q1 and small q2, then it holds for q capital 1 and q capital 2, because we subtract the same two terms, 1/4 p minus 1/2 p prime. Well, and so in what follows, we will discuss these two equations. Well, step number 2. So suppose, let's denote that two consecutive zeros of the function x of t by a small and b small. So suppose a and b are two consecutive zeros of the function x of t. So let it be u of t then. U of t. So I'd like to recall that u of t and x of t have the same zeros. And v of t and y of t have the same zeros also. Zeros of u of t or x of t, which is the same. So I mean that u of a equals u of b equals 0. Well, so let it be a figure. So u of a, so this is u, and this is t. U of a equals u of b equals 0 by lemma 1. They are simple zeros. And if we suppose that u of t, so it can be greater than 0 or less than 0. So without loss of generality, we suppose that u of t is greater than 0 for t between a and b. Then I claim that u prime of a is greater than 0 and u prime of b is less than 0. So I need to know the derivatives at the points a and b, and I claim that u prime of a is greater than 0 and u prime of b is less than 0. Okay, so how to prove this? They cannot be equal to 0 because of lemma 1, and u prime of a can be found as the limit of u of t minus u of a over t minus a, where t approaches a. Plus. So this is t. So we know that u of a is 0 and u of t is greater than 0. And t is greater than a. So you can see that the quotient, this quotient is greater than 0, and the limit is greater than or equal to 0. But since it cannot be equal to 0 because of lemma 1, it follows that u prime of a is greater than 0. Similarly, we can prove that u prime of b is less than 0. So this is the first assumption, and so the second one, the second assumption, let's consider the function v of t. Let's consider a solution of this equation. Suppose, on the contrary, that v of t has no zeros on AB. And assume for definiteness that v of t is greater than 0 on AB. It can be less than 0, and the reasonings will be the same. But we will suppose that v of t is greater than 0 on AB. And we suppose that it has no roots. Well, now step number 3, and this will be the last step. Step number 3, we will write two equations, u double prime plus q1 of t u equals 0, and v double prime plus q2 of t v equals 0. And we will multiply the first equation by v, the second one by u, and subtract them. And we will get the following: u double prime v minus v double prime times u plus q1 of t uv minus u2 of t uv equals 0. Let's discuss all the terms of this expression. So I claim that u double prime times v minus v double prime times u equals u prime v minus v prime u prime. So is it true that the derivative of this function is equal to the left-hand side? Can you check? Let's check this. So if we differentiate this expression, we will get u double by the product rule, u double prime times v plus u prime v prime. This is the derivative of the first term minus the derivative of the second one, v double prime times u minus v prime u prime. You can see the same terms, and we can cancel them out. And so now you can see u double prime times v minus v double prime minus u. This is the same as in the left-hand side, right? So this equation can be rewritten as u prime v minus v prime u prime equals, so not equal to, plus. So uv is a common factor for the last two terms. So it will be plus q1 minus q2 times uv equals 0. Or if we move the second term to the right hand side, we will get the following: u prime v minus v prime u prime equals q2 minus q1 times uv. Okay, so we have obtained this. And now we will integrate both parts from a to b. Integrate both parts. So I will use that part over the blackboard. So the integral, so the first integral, so the derivative, if we integrate the derivative, we will get this expression in the left hand side. So in the left hand side we will get u prime v minus v prime u from a to b equals the integral from a to b u2 minus q1 uv dt. Now let's substitute upper and lower bounds, upper and lower limits, and we will get a u prime of b, v of b minus v prime of b, u of b, u prime of a plus v prime of a, u of a. Let's simplify this. We know that a and b are zeros of the function u. Look here. U of a equals u of b equals 0. So this is 0. And this eliminates the second term. And u of a is also 0. This is also eliminated. So on the left, we have the following: u prime of b, v of b, minus u prime of a, v of a. Okay. What is the sign of this expression, positive or negative? Or neither, or it cannot be determined. What is the sign of this expression, positive or negative? Huh? All of it.
Depends
yes.
on the u tag a, the a. If it's greater.
Okay. So what about u prime of b? So u prime of b is less than 0. It was proved there. U prime of b is less than 0. Less than 0. What about u of b? So v of b. So v of b is positive on AB. So it is positive on AB. So positive. So this is positive, positive, u prime of A. Positive, but it is subtracted, right? So it is positive and positive, positive.
But doesn't like u tag b multiplied by v be, is it multiplication, right?
Multiplication, yes.
So if it's minus multiplied by plus.
Well, minus by plus gives us minus, and this is also positive, but is it subtracted? So it is negative, right? Less than 0. But what about the right hand side? The integral from a to b, q2 minus q1 times uv dt. So what about q2 minus q1? So q2 is greater than or equal to q1. So we'll look at the statement. So look here, step number 1. So it is positive. It is positive, yes, positive. next or equal to 0. So what about u times v? They are both positive by assumption. V is positive and u is positive. U of t is positive if t is between a and b. So they are both positive. So this is positive. So this is positive and this is negative. And so this is a contradiction. We come to the contradictions, and this proves our theorem.
Yes.
This is Sturm comparison theorem. Now I suggest to have a break, and after this I will show something, right?
I have a question. For Laplace transformations, will you give us a table for the transformation?
Right, so you will need only one